Constructing the magnet is an interesting thing. I have noticed that the magnet was actually quite big. Let's go back here. This is the magnet here. There seems to be quite a lot of it. So if we just go along here and we look at what's required. Now this is a diagram. You can shut your eyes here for a minute while I waffle on about physics. This is a diagram out of one of my textbooks. You wind a solenoid like this, you put wire around there, and you can derive, using this construction here, an equation for the magnetic field inside. B equals mu naught Ni. Mu naught is 4 pi times 10 to the minus 7. N, the number of turns per metre. I is the current. And we can use Ampere's current law to estimate roughly what sort of magnetic field will result. If we wanted 1 Tesla magnetic field, then we need 8,000 turns per metre from this equation here. And if we require 100 amps, we need 4 AWG wire, which is quite thick, 5 millimetres in diameter. The resistance of that is 90 ohms, and the power dissipated at 100 amps will be 190 kilowatts. So that'll get quite hot. And also, because this is rather thick wire, we need a coil 400 metres in diameter. Well, this is clearly impossible. So what do? The answer is we use superconducting wire. And what happens with superconductors, this is temperature along the bottom in degrees Kelvin, and this is resistivity, ohm, meters, don't worry about that. As we go up here, the resistance gets higher. As we decrease the temperature of a material, then its resistance goes down and down and down and down. And in some materials, you reach a critical value, and the resistance suddenly drops to 0. Not just very low, but 0. In fact, you can make a completely circular wire, make it superconducting, this is what superconducting is, and you can start a current in that and the current will flow for months and months and months. It will eventually stop because of magnetic losses and eddy currents. So typically they use a material, niobium titanate here, which has got a critical transition temperature of 10 degrees K. So that's minus 263 degrees, approximately 10 degrees above absolute zero. You've got to cool it down there. That's why these machines are so large, because they have to have all this cryogenic cooling there. This bloke, Paul Callahan, some of you may have heard Paul talking on the wireless. He used to talk a lot on Saturday mornings. And he has a firm which markets commercial MRI machinery, and mainly they're for looking at pieces of machinery. And he's got a series of 10 videos on the web which are really very informative, and I'll just show you a little bit of one of them.
My name is Paul Callahan, and in this series of videos we're going to be looking at some of the basic ideas behind nuclear magnetic resonance and magnetic resonance imaging. And to help us look at those ideas, we've got this apparatus here behind me. It's a very simple nuclear magnetic resonance
So we won't be able to go through all his ideas at the moment because it takes about an hour and a half. But they're very informative videos. If you want to understand, I'm sure none of you do, but if you did, this is the place to get this stuff. Well, here's some questions. An MRI scan takes between 15 and 45 minutes, and you have to keep still. What does it sound like? Did yours sound something like that? Yes. There's another. The machine's very annoying. You can see why some people find this a bit alarming when all of these noises, and they're quite loud. Did they give you pads to put on?
No.
No, the modern ones are quiet, but the early ones would. What causes this? It's the magnets are pulsed with current pulses, and the wires contract and expand. And what you're hearing is the expansion and contraction of the wires. And it happens very fast, so they ring and they go bang, 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 bang. But the detail that MRI scans can show are absolutely astonishing. Here's a human head. By processing in different ways, you can see, well, take the top of the head off, there's the brain. Very interesting. You can cut the brain in half, See bits in the middle. Take away more skin. Yes, we can rotate it. See what the brain's made of. MRI is very good at imaging soft tissue, not so good at bones and hard tissue. Here are the eyeballs. Yes. Very good on the skin. And so forth. Well, we'll stop that one. Go away. Because they have very high magnetic fields, things can get stuck on them. Here's a chair that got contracted to an MRI machine.
Oh, yeah, we get all that. No. Yeah. Be careful.
That's being pulled into the machine by a magnetic force. It's just a very powerful magnet. There are lots of horror stories on the web. On one occasion, a small child had been assaulted and they took her into an MRI room, this is in the US, to get a scan. And the policeman who'd found her went into the MRI as well, and he stood a bit close, and his holster was unbuttoned, and his gun flew out of the holster, flew into the MRI machine and went off, bang. Fortunately, nobody was shot, but things like that happen. Here's a demonstration with an oxygen bottle. So everything in an MRI room has to be non-magnetic. And if you're put into one of these machines, they look at you very carefully to make sure you're not wearing a magnetic wristwatch or anything like that. And if you're having some types of, if you've got some magnetic material like I've got a titanium hip, they really don't want to know you. Alright, CAT scans, CT scans. Who's had a CT scan? This is a different machine, and it does use X-rays, and it looks a bit imposing too, but not quite as imposing. It's got a hole in it, a donut hole like the MRI machine, but the hole is in a much flatter thing. And the patient moves through the hole during the scan. How long did your scan take?
I can't remember, but it seemed only, well...
It's seconds, isn't it?
It's only seconds.
It's only seconds, yes.
The preparation for it was the longest
yes.
and most traumatic part of it.
And you lie there, I've had several actually, and you lie there the first time and they do something and you think, well, when does it start? And they say, oh, it's over, mate, you can go back now. And you're really not aware of it. So, here's an well, I'll try to play this animation of what happens.
CAT scans produce 3D images of the inside of the human body. The instrument uses an energy source that emits a fan-shaped beam of X-rays and a receiver or X-ray detector on the exit side of the patient that records the snapshot X-ray. Multiple snapshots collected during one complete rotation
Very low sound on this one.
to create a cross-sectional image.
X-ray source. 5 X-ray receivers.
Move through the machine in increments with an image slice being
Spins around.
each position. Every rotation, here speeded up, yields an image of a new slice as it moves through the length of the target. In this case, through the head of the person who is lying in the chamber.
Okay, we'll stop there and go on a little bit, because what I want to show you is what actually lives under the covers. Before these things start, you hear it winding up? Remember that? This is what it's doing. It winds up to about 4 or 5 revolutions per second. And then your body is moved slowly through that, and it scans the whole body in a spiral. Like this. So the patient is moved through the machine, and it gets scanned in a spiral. These machines also produce astonishing pictures. This is a skull. Notice that the bone detail is very much better than in an MRI. This is a commercially produced one just to show what commercial software can actually do. We might just enhance that a little bit. So now we're right inside the skull. We can move around looking at what's in there. Well, you can imagine what a diagnostic help this is, if people have had things bashed on their skull. Alright, let's know that one. We'll look at another one. So there's skin. There's bone inside. It's very lifelike. What we're doing here is like walking around something from every angle, so that all the information about what it looks like from every angle is captured somewhere. And because it's done with X-rays, we can also see through it, see inside. Okay, so it looks like that. We'll stop that and we'll go on to this abdominal view. Now, I think this one is quite astonishing. So here's the liver. We're looking at somebody's liver, and we can move it around with this specialised software, look at it from different directions. We can change its colour balance. We can look inside the liver. Now you can see there's a mouse on the left-hand side here moving stuff. Here are the blood vessels inside the liver, which we can see. Now we'll put the skin back on, and we will, what do we do next? We're looking at the detail of something else, some of the tissue inside. We'll advance a little bit, because we don't have time. Alright, so here's a liver, here are both the livers. Two livers.
No.
Kidney. The kidney. Is it? Oh, it's kidney. Sorry, it's kidney. Yes, it says liver and kidney. And they're colour-coded, the machine obliging. Oh, there's a bit of skeleton. Isn't that amazing? Ah, more skeleton.
More back and ribs.
Oh, yes. And I think if we're lucky, we see over here something. Oh, yeah, there's the other kidney. I knew another kidney came.
A little tube between the two of them that feeds the belly.
Toe. What's it going to do now? Oh, we'll advance a bit more. So it goes. But so isn't that amazing? That's astonishing. They've also used them to look at the interiors of Egyptian mummies, which of course you can't really unwrap to look at. So here's a CT scan of a mummy in some museum, and indeed there's a skull, some of the teeth are missing. There it is. And so it goes. Alright. So CT scans are just astonishing. X-ray radiation levels, people often ask me, well, are they dangerous? The maximum safe dose is normally thought to be 50 rem. Now rem is a funny unit. It stands for Roentgen equivalent man, and it's a combination of two factors. The total dose in the amount of radiation received in joules, and the characteristics of the body to that radiation. And the doses greater than 200 cause blood changes and illness, and over 1,000 rem may be fatal. And if you've got one of those in a nuclear accident, and that's typically what the people right at the centre of the Nagasaki and Hiroshima bomb attacks did, then you die. But if you look at what happens in practice, 0.5 of a millirem, that's 1,000th of a rem for a dental X-ray. So that's not really very dangerous. Going down to 2,000 millirems or 2 rems for a CT scan of the heart. But remember that people have found less than 50, no bad effects have ever been detected. Although people are still arguing about prolonged exposure. Who's had an ultrasound scan? Well, they're quite fun, except that you can see what's going on. Absolutely non-invasive, very quick, and the frequencies used, however, are a bit astonishing. They're between 2 and 18 megahertz, so you can't hear them. It's called ultrasound. It really is ultra. It's very high frequency. It's really radio frequencies, well over human hearing range. Dogs can hear to 60 kilohertz or so, mice to 90, and dolphins up to about 150 kilohertz, and bats can, it is thought, hear up to about 800 kilohertz as well. They travel at the same speed of sound in air, and the wavelengths are typically about 1 millimetre. So that's much lower than the corresponding wavelength would be of a radio signal, because the speed is much slower, you see. And the attenuation is quite large going through tissue. It's the frequency times the range in centimetres, the round trip range, divided by 2. And so the attenuation is approximately 10 to 70 dB. And the machinery looks like this. They typically wheel up this equipment, and so the portable could come up alongside your bed, and there's a computer screen where you see the results, and the transducer looks like that. The technology is very interesting because the transducer itself, which looks like a shaver, uses beamforming technology. It's got a number of different elements, and the signal arrives at the elements at different times. In this case, there's a delay in the centre, so this causes a pencil beam which is focused at a particular point. And many of these modern ones are actually adaptive. They look at what they're looking at, like modern video cameras, and they adjust their focusing to get a sharp image. And the receiver is similar, except it doesn't do any beamforming, but it has to have a variable gain amplifiers in it, because the signal coming back from different depths in the body can vary over a range of 60 dB or so. You've probably seen, has anybody not seen one of these? This is what one looks like. This is a baby inside a mother's womb. So there's the baby inside there. It's going to be moving around. Hasn't started moving very much yet. This is 12 weeks old baby. So who's actually seeing one of these on the screen while it's being done to them? It's quite interesting, really, although it's quite hard for a lay person to work out. Here's the heartbeat. So that's the baby's heartbeat. Now he puts a cursor between two of the peaks, and he finds that the heart rate is 153 beats per minute, which is typical for a baby. And so forth. You can see the baby here lying on its back, and it's going to do some gymnastics in a minute. We'll just move that on a little bit. Come on, baby, go. Go. Something is pulsing there. Now the baby is moving around inside. Come on, baby, move. Yes, there's little feet waving in the air. Of course, only roughly 50% of the human population has experienced this. Can't say I have. I'm often asked about the physics of eyesight, which is good because we all have eyes, hopefully. Here's a picture of an eye. Here's a video. What happens in an eye?
Light rays enter the eye through the cornea, pupil, and lens. These light rays pass through the vitreous, a clear gel-like substance that fills the middle of the eye. The light rays are focused on the retina, a light-sensitive tissue lying in the back of the eye. The macula is a very small area at the center of the retina that gives us our fine pinpoint central vision. The area of retina surrounding the macula gives us our peripheral or side vision. The retina converts the light rays into signals that are sent through the optic nerve to the brain.
Okay. Macula is the most sensitive part. Probably most of you have been checked with one of these Snellen charts for eyesight. And if you've been told you've got 20-something vision or 6-something vision, 20/20 if your optometrist is an old style foot and inches person, 6 if he's talking about meters. What does this mean?
You hear the term all the time, but what does 20/20 vision actually mean? 20/20 means that you can see at 20 feet away what a person with normal sight can see at 20 feet. The number is an indication of your visual acuity. If you can only see the top E, that means you can see at 20 feet what a person with normal sight can see at 200 feet. This is called 20/200 vision. If you can read this row, you have 20/40 vision. Normal sight sees at 40 feet what you see at 20 feet. When you're able to read this row, called 2010 vision, it means that you can see at 20 feet what normal sight can see at 10 feet. This means you have exceptional sight.
Alright, so much for that. So there's a Skillin chart. They're in every optometrist's office. Cats have very much poorer vision than we have, 2200. Hawks are very much better than we are, 20/2. So they can see at 20 feet the details that we would only be able to see at 2 feet. And that's because they have a lot more fibre receptors in the portions of their eye. Their eye is specially designed for that. When you go to be checked for spectacles, you will be put in on one of these machines, a phoropter, and often the optometrist will take a photograph of the inside of your eye, which looks like that. These photographs of the insides of my eyeballs made by my optometrist. Here's my excellent left eyeball, which is quite healthy, but alas, my right eyeball covers from macular degeneration. These ominous darkened areas. Remember, if we think back to that video, the macula is the most sensitive bit in the middle. And this is very common with old people, which is a bit of a bummer, but my eye still works reasonably well, so what the heck. They check for macular degeneration by looking at that. Okay, close one eye, look at that screen. If you see something like this, or distortions, and I see distortions with my right eye but not with my left hand, that means you have incipient macular degeneration and you should go and get a check. My optometrist said everybody should get a copy of this chart. You can download one from the internet, take it on the side of their fridge, and every morning come in and do that and see whether your eye is still working all right.
You just get a bit of graph paper and put a dot in the middle of that.
Oh, yeah, but that's cheating. You could do that. I think we won't show this video, we all know what accommodation means. Accommodation means like a camera. You can, I know radio hands understand that. The ability to focus from near to far. However, accommodation changes with age. Now, we're all familiar with this. A baby can focus up, down to about here. And this is called the ratio of that distance to, well, the accommodation, we won't go into that. What happens as you get older, as you go on in years, then we follow this curve roughly, and your near point goes down and down and down. Some of you will have got to that stage where you realise your arms are no longer long enough to read the herald, because your near point has gone away. Mine started doing that when I was about 48. Happens with some people a lot earlier. Eventually, this goes negative. And in fact, my eyes now naturally focus beyond infinity are at a point inside my head. So when I take my glasses off, I can't actually you look a lot better when you're fuzzy, but I can't focus properly at all. So here's a formula that optometrists use, Hofstadter's formula, 18.5 minus your age in years divided by 3. That gives you the approximate formula for accommodation amplitude. That's where your near point approximately is. Hyperopia and myopia, nearsighted and long-sighted people, and this just says if you are long-sighted, as I am, then you need effectively a magnifying glass, you need convex lenses to focus to infinity. If you're short-sighted the other way, then you have concave lenses. And if you have graded spectacles, how many of you have graded spectacles? They're great, graded spectacles. Then what you have is a physically impossible situation because you're making a lens which has got a different focal length as you go down. The focal length is designed to focus naturally at infinity when you look through the top part and at a distance of about that much when you look through the bottom part. Unfortunately, these two criteria are completely incompatible. And so what they do instead, they fudge it at the edges. So if you have graded glasses, they work fine in the centre of the vision, but as you move down the lenses, they get fuzzier and fuzzier out towards the end. Do you find that, Peter? Down towards the edges. And that's because it's physically impossible to do this. Well, it's just a little bit something you all know about. 1 upon V equals 1 upon U equals 1 upon F. I don't have to tell radio hands what that means, focal length. But a number of people have asked me, what does the optometrist write down when he writes my prescription for spectacles? What are these things called diopters? Diopters are 1 on the focal length in meters. Okay, so here's my spectacle prescription. It says I have 2 eyes. Yes, I believe it. A right eye and a left eye. Let's look at the left eye first. The left eye says I need a lens of 3 diopters, that's a focal length of 33 centimetres, to pull my comfortable focus back to infinity. So I have to wear that all the time. And for reading, I need an additional 2.5 diopters, so that's 5.5 diopters, so that brings the focal length down below 20 centimetres. And for intermediate vision, I need 1.75 on top of that. So these are the numbers that go off to Singapore by email, and 4 days later the spectacles come back from the clever little man in Singapore who has made them. My right eye is much worse. It needs 4 diopters, or a lens of focal length 25 centimetres for infinity. Again, 2.5, that's the standard measure that the optometrist adds for near vision, and the intermediate 1.75. But there are 2 additional parameters in here, cylinder and axis, because this eye also has astigmatism. And astigmatism means that the focal length of your lens is different for images which are in that direction and images which are in that direction. So, for example, across, you can't image correctly. You need different focal lengths for each part of the cross. Now, to correct that, you can put in a cylindrically shaped portion of the lens, and here it says the axis is 45 degrees to the normal, and the power is minus 0.25 of a diopter, so it's a weakly diverging lens. PD is the pupillary distance. That's the distance between your eyeballs. There are 2 numbers there, 65 and 62. 65 is the distance between your 2 pupils when you're looking straight ahead. 62 is when you cross your eyes when you're reading up close. And this is necessary to design the spectacles correctly to make the frames properly. See, so it's quite simple.
What's the intermediate, Gary?
Intermediate is for intermediate vision. If I'm looking at something 2 or 3 metres away, that's the middle part of the spectacle that I would use. See, and people will agree, if I look into the distance, we're always looking into the centre. But if I go up to a notice board, and you'll notice as people go to a notice board, and they'll start doing this. They'll look like that. And that's because they can only read some of the notices through the lower portions. And so these people go around with their heads cocked in strange like that. It becomes completely automatic after a while. Although for a while, I know I was running quite a lot when I had my first set of these spectacles, and it was very confusing because my feet looked a long, long way away, and I would get seasick running up the road. So I took them off, and then I'd hear people, hi Gary, and people would go past in the cars, and I couldn't see who they were. So I put my spectacles on again, and then I felt sick again. So I think that's all I'll say. Thank goodness, I've talked long enough.